Welcome to the Data Science Seminar from the University of Washington's eScience Institute. As part of the University of Washington, I want to begin by acknowledging the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. Before we begin, for those who are joining us online, I'd like to mention that we're using the Zoom webinar, so you can ask questions using the Q&A feature on the bottom of your screen. For us in the room, put our phones on silent, which I will do in a second. I'm excited today. This is the final data science seminar of the quarter, but this talk is actually co-sponsored by the Environmental Impacts of Data Science Working Group at the University of Washington, and I'm one of the leaders of that group. And if you're interested in learning more about that, come see the eScience website. Our speaker today is Priya Danti. She is a PhD candidate and in computer science and public policy at Carnegie Mellon University. She is also co-founder and chair of Climate Change AI, an initiative to catalyze impactful work in climate change and machine learning. Her work focuses on machine learning for forecasting, optimization, and control in high renewables power grids. Priya is a member of MIT Technology Review's 2021 list of 35 innovators under 35. And she is a recipient of many, many awards, including the DOE's CSGF fellowship, in addition to many others. And with that, I'll turn the talk over to Priya to talk to us about tackling climate change with machine learning.
All right. Yeah. And thanks so much, Dave, Nicoletta, Emily, if you're there, and others for organizing today. So today I want to talk a bit about the connections between climate change and machine learning. And I'll primarily focus on the ways in which AI and machine learning can help us to address climate change, but also talk about various other axes in which by which these topics interact. So starting off, climate change is, of course, one of the most pressing issues that we as a society are facing today, and we're already feeling its effects, from storms to droughts to fires to flooding. These impacts are being felt globally, and they are disproportionately being felt by the world's most disadvantaged populations, which creates a real imperative to act very quickly on this issue. In particular, according to the UN Intergovernmental Panel on Climate Change, we as a society need to hit net zero greenhouse gas emissions by 2050, which means that in practice, a lot of the major policy, engineering, and social sciences efforts need to be set in place over the course of the next decade. And yet, given this really, ambitious goal, this goal that is sort of necessary to stave off some of the worst impacts of climate change, we still see trends where global greenhouse gas emissions are increasing year after year. So again, this is something we have to act really quickly on in order to avoid some of the worst impacts of climate change. And when I talk about addressing climate change or tackling climate change, there are actually two major axes associated with this. So one of these is climate change mitigation, which means reducing the amount of greenhouse gas emissions that we put into the atmosphere in order to reduce the extent to which climate change even occurs. And so when I talk about this goal of net zero by 2050, that is actually a climate change mitigation related goal. But in addition to that, we have unfortunately already locked in some amount of climate change due to greenhouse gas emissions we've already put in the atmosphere and that will continue to stay in the atmosphere for several, decades, centuries. And so in addition to climate change mitigation, we also need to take strong actions to adapt to the effects of climate change, to build resilience to the consequences of climate change, like the storms, droughts, fires, so forth, that I mentioned earlier. And this will require basically, local actions at a global scale, as each individual community contends with the different kinds of climate risks that it will actually end up facing. One thing that's really important to think about as we think about both climate change mitigation and adaptation is that taking these kinds of actions and addressing climate change in this way isn't an on-off switch. So when I mentioned, for example, this climate change mitigation goal of net zero by 2050, it's not a matter of, well, if we hit net zero by 2050, we're good. And if we hit net zero only by 2051, then we've completely failed. In some sense, the more greenhouse gas emissions we can reduce earlier on, the fewer effects of climate change we will see. And as a result, the less aggressive adaptation actions we will need to take in order to deal with those effects. So in some sense, this target is not an on-off switch of we succeed or fail. And so people will ask, well, are we going to hit the net zero by 2050 target? And if not, should I just not work on this issue at all? That's definitely not the way to think about it. Definitely every ounce of action that we can take today will make the situation going better going forward. So when we think about climate change as a whole, there are obviously many different avenues of action that one can take. We will need all of these avenues of action and tools coming from AI, engineering, policy, the social sciences, and so forth. But today I want to focus in on AI. What is the role that AI actually plays in this broader picture, both the good and the bad? So in particular, AI has been proposed as a way to actually bolster or accelerate many different strategies to address climate change through both climate change mitigation and adaptation. And that's actually, primarily what I'll talk about during today's talk. In addition, though, AI is a general purpose technology that can be used to accelerate all sorts of applications across society, including those that increase emissions, for example, by accelerating emissions intensive industry. So I'll talk really briefly about that as well. There are also lots of applications that we might not think of as relevant to climate change when we at first blush, things like autonomous vehicles or targeted advertising, where AI is actually a very fundamental component of these applications. And yet these applications can have really large effects on climate action, either positive or negative, depending on how exactly we go about them. And so it's worth bearing in mind as we're actually developing applications in cases where we can actually shape the trajectory of these applications in a way that is aligned with climate change, we should be doing that, or aligned with addressing climate change, I should say, we should be doing that. And then, of course, AI itself, AI algorithms themselves run on computational hardware, and both the electricity used to power the computations and the hardware itself have emissions implications. So it's worth thinking about, again, what are these impacts? So I'll dive into all four of these at some point throughout the course of the talk. But for most of the talk, I want to focus in on this first axis, which is how exactly can we use AI to help bolster climate change mitigation and adaptation efforts. And so in this first big part of the talk, I'll both give a big overview of sort of how we should think about where AI can plug in. And I'll also give a quick overview of my own work in this area, which focuses on AI for electric power systems. So diving right in, about, I guess, 3 years ago at this point, a group of us wrote a paper called Tackling Climate Change with Machine Learning that attempted to detail the various ways in which AI could contribute to climate change mitigation, climate change adaptation, and also to cross-cutting societal strategies and tools, things like policy, the social sciences, to finance and so forth, that actually enable the implementation of climate change mitigation and adaptation strategies. For those of you who are interested in this area, I definitely encourage you to check out the paper. That said, it's somewhat long. It's on the order of 50 to 100 pages. So I also at the top of this slide have put a link to a set of interactive summaries that you can actually play around with to get a sense of the contents of the paper and focus in on specific parts. And in that paper, what we do is we note that the sources of greenhouse gas emissions from around the world are very diverse, right? This chart from the World Resources Institute basically shows the sources of greenhouse gas emissions in 2016, where the first column is broken down by sector. So you can see electricity and heat make up about 30%, transportation is about 16%, agriculture 12%, land use and forestry change 7%, and so forth. So we take these different categories of where emissions come from and try to identify, what are the applications of AI to actually reducing emissions in these particular sectors. And we similarly went through a similar kind of exercise on the adaptation side, in this cross-cutting tool side. What are the different aspects of adapting to climate change? What are the different kinds of policy, finance, social sciences tools we need to actually implement these kinds of changes? And where can AI plug into all of these things? And the result was, dozens and dozens of different ways in which AI and machine learning can actually plug in, with sort of just an overview of the figures in the paper on this slide. Now, I'm not, unfortunately, in the course of this talk, going to be able to talk through, all of those dozens of applications. But what I hope to do today is give a few examples of the kinds of applications that come up. And in the process, also maybe highlight some recurring or cross-cutting themes that can hopefully help you kind of understand or imagine other ways in which you might use your own skills or your own area of AI, for example, to actually plug in to this broader ecosystem. So the first theme that comes up is gathering information. So there are lots of situations in which there are large raw sources of data that are available, things like satellite imagery and aerial imagery or large bodies of text. And where these sources of information in and of themselves are really hard to analyze at scale, but potentially contain some information that is useful to inform some kind of climate-related strategy. For example, as global policymakers actually try to set various kinds of emissions targets and goals over time, these emissions targets are actually set based on sort of self-reported voluntary emissions reporting databases. And there are, lots of concerns and, geopolitical issues around, which country trusts which country's emissions reports and all of that. So a kind of coalition of organizations called Climate Trace noted, well, we have a lot of satellite imagery and we also have some on the ground sensor data. Can we somehow turn this raw information into an independent and auditable inventory of global greenhouse gas emissions using tools from AI and machine learning? So this is one example of a place where maybe there are reasons that our existing data has various, political implications associated with it or is somehow incomplete, but we can take, a large source of data like satellite imagery and use AI and machine learning alongside other tools to translate that into information or proxies for information that is more actionable that we can actually, use to make climate change related decisions. The image on the slide is another example here of using satellite imagery for crop cover mapping. And this is basically to understand how global crop cover and global farming is actually changing, for example, as a result of climate change and what we can do about that. So there are several governmental programs like NASA Harvest and in Europe, the Copernicus Land Monitoring Service, or NGOs like GeoGlam, companies like Indigo that are actually doing this kind of work using satellite imagery and on the ground sensor data and turning that into actionable information about crop cover mapping. And then a last example I'll give here is on the policy and text side. So there are many different policy and text documents that reflect the different kinds of policies that different jurisdictions have made to address climate change or related issues. And if you're a policymaker who's looking to actually form policies in your own jurisdiction or understand what worked or didn't work in the past, you might then try to do a literature review of all of the policy documents that have existed in a related area. And this can be, of course, a really overwhelming task given the amount of policy documents that exist in the world. So a nonprofit called Climate Policy Radar, to give one example, is actually currently using natural language processing techniques to analyze policy documents at scale in a way that can hopefully glean actionable insights for decision makers who themselves are now trying to form new policies, enable them to do it in a more effective manner. So these are a couple of examples of this broader theme of where we can use AI and machine learning to potentially provide information or proxies for information based on large amounts of data, raw data like satellite imagery or text documents. Another recurring theme that comes up is maybe unsurprisingly forecasting. There are lots of settings where having some kind of foresight can help make a better decision in a way that helps, manage a certain set of infrastructure or something in a better way, in a way that enables us to reduce greenhouse gas emissions. So one example of that is renewable energy. As we put more solar and wind power onto the electric grid, the output of the solar farms and the wind farms that we actually put onto the grid varies based on the weather. And this actually poses some new challenges for power system operators. So those who are operating the electric power grid need to maintain a balance between electricity supply and demand almost exactly at every single moment in time. And as we start to enter a power grid, we're now on our electricity supply side, because we're installing solar and wind power that can vary based on the weather, we have some uncertainty. Power system operators are investing a lot of effort into trying to pin down better forecasts of the solar and wind power in order to enable them to maintain this balance between supply and demand more effectively, and as a result, not break the power grid by not maintaining that balance. So AI and machine learning have been used to take historical data on, for example, weather, even video data that is, you can put a video next to a camera next to a solar farm that's pointed up to track cloud cover. So people have used AI and machine learning to sort of ingest these heterogeneous sources of data and use that to provide both short and medium term forecasts of renewable energy. So the image on the slide is from a nonprofit called Open Climate Fix that is doing this kind of work and actually helped to double the accuracy of the forecasts used by the UK power system operator in order to enable them to manage the renewables on their grid better. And this theme of forecasting, again, maybe unsurprisingly, comes up in a lot of different contexts. For example, there are folks who are using AI and machine learning to forecast the demand for transportation, or to forecast where and when extreme events will occur using a combination of machine learning and physical modeling in order to help either shape transportation planning and policy, or to help different entities adapt, again, to the effects of climate change by providing early warning as to when an extreme event would occur in order to enable a set of stakeholders to actually react to that. So these two themes of gathering information and forecasting deal with somehow using AI and machine learning to provide information to a decision maker, whether that's a human decision maker or an automated decision maker, in order to enable them to make a better decision. There are also many cases where AI and machine learning is in some sense itself the decision maker that is doing something to actually control an underlying system. And this can be, done in ways that actually, again, facilitate climate change related goals. For example, if we think about the heating and cooling systems in our buildings, residential and commercial buildings make up about 20% of global greenhouse gas emissions, depending on how you slice and dice it, and heating and cooling is about half of that. But the way our heating and cooling systems are operated today is really inefficient. It's based on really rough heuristics. It's based on very little understanding of the physics of any given building or of the occupancy patterns of any given building. So controlling the heating and cooling systems in buildings in a more dynamic and data-driven manner that's actually responsive to the situation on the ground can actually improve or reduce the amount of energy that's used to actually heat and cool the building in the first place, while still maintaining various properties like thermal comfort in a building. So AI and machine learning has been used to actually provide automated control strategies, for example, through reinforcement learning, that actually take in information from sensors about how a building is responding to various kinds of control actions that you would do with the heating and cooling system, and then using that to actually improve the efficiency of the control system in the first place. So there are lots of examples of this in kind of, again, residential and commercial buildings where, there are companies like, Nest and Arup and various companies that actually use AI and machine learning to modulate heating and cooling in, for example, homes or schools. But this also occurs in sort of bigger industrial settings. So for example, there was a kind of, big, famous headline or application where DeepMind used a reinforcement learning algorithm to control the heating and cooling systems in Google data centers in order to continue to cool the data centers, but in a way that actually used a lot less energy. So this example of, improving operational efficiency by optimizing a system more effectively comes up not just in heating and cooling, but also in things like actually optimizing the routes of global freight transportation systems as we transport goods from one place to another, and also optimizing refrigeration systems that are used to store produce or to keep produce good in a way that otherwise helps reduce food waste. Similarly, in order to kind of, increase the efficiency of operational systems, another theme that AI and machine learning is often used for is predictive maintenance. So kind of before a system breaks, or right after it breaks, providing some information to pinpoint that source of breakage and actually patch up the issue with the systems in the first place. So one big example of this is the use of AI and machine learning to actually address methane leaks. So as we transport natural gas from where it's extracted to where it's used, for example, natural gas is used to power, natural gas power plants on the electric power grid, or it's also used for heating and cooling systems in many homes. That natural gas is transported along pipelines. And when these pipelines break, this natural gas in the form of methane actually leaks out into the atmosphere. And methane is a really potent greenhouse gas. Depending on the horizon on which you're evaluating this, it's 40 to 100 times more potent than carbon dioxide. So preventing the leaks of methane from these pipelines, either proactively or as soon as they occur, can actually be a really huge source of reduction of the greenhouse gas emissions we're putting into the atmosphere. So AI and machine learning have been used to analyze a combination of drone and aerial imagery and sensor imagery that's outfitted on the pipelines and in compressor stations, to actually identify the size of leaks that may already be occurring in order to pinpoint maintenance, or even to preemptively identify where a leak may occur so that one can sort of shore up the pipeline infrastructure. This theme of predictive maintenance also comes up in a bunch of other places. So for example, Deutsche Bahn, the German train operator, uses AI and machine learning to fix various faults in their train system to make their infrastructure more resilient and have the trains run on time and move faster. And this basically makes rail transportation and low carbon rail transportation a more viable and attractive option compared to other forms of transportation, by basically allowing the train system to run more quickly. So while those last two themes focused on operating, real world systems, there are also lots of ways in which AI and machine learning can help us, accelerate the process of developing new technologies and new systems, so accelerate scientific experimentation. So for example, right now there are lots of efforts to create better batteries, where the definition of better depends a lot on the application that you're using the battery for. For example, batteries are, of course, a key component of electric vehicles. And there's this, a lot of efforts to try to, improve the amount of energy that a given battery can hold, to reduce its weight, things that make it sort of better suited for installation within an electric vehicle, or, make the car sort of drive farther once you put the battery in there. Similarly, batteries are often put on the electric power grid to help, manage the variability in renewable energy. And there you want batteries that you can sort of cycle, you can charge and discharge a lot without necessarily degrading the battery a lot. So there are lots of efforts to create better batteries for many different applications. But the challenge here is that the time it takes to design any given battery and test it out is really, really large. So if I want to design a battery, I look at the outcomes of various past experiments that I've tried. I use that information and maybe my own knowledge, if I'm sort of a scientist who's working on, battery development, to say, okay, maybe I should try this particular battery design next. I then synthesize my battery. I test out that battery, which is a process that can take months to years. I see how that experiment went, and I, start the design cycle over again. And what certain companies like Aionics, which was started out of Stanford, I believe, have started to do, have said, well, can we somehow use a combination of AI and physics, a pure AI and machine learning and physics informed modeling to actually analyze the outcomes of our past experiments and then recommend which experiments are the best to try next in order to then cut down on the number of design cycles, and as a result, just speed up the process of discovering a battery in the first place. So this is one example where AI and machine learning have been used for, next generation, for accelerating scientific experimentation in order to help create batteries. But this theme actually comes up in a lot of different places. For example, in the design of electrofuels, or in the design of carbon sorbents, which are basically, you can think of them as sponges for sucking carbon dioxide out of the atmosphere. And then last but not least, on the kind of, that was accelerating scientific experimentation is sort of one aspect of how AI can help science and engineering in the climate change area. Another aspect is by approximating time-intensive simulations. So there are many scenarios in climate and energy where you have some kind of big physical simulation that you're running in order to get some kind of insight. For example, you might be running a large-scale climate model to try to understand how the climate will change. You might be running a large-scale energy model to try to figure out how you actually build your energy infrastructure over time. Or you might be running a large-scale city planning model to understand things like how the wind flows through your city and how that should influence how you actually design or retrofit aspects of the city in a way that's more energy efficient. So these simulations are, again, really large and time intensive, and AI and machine learning have actually been used to try to approximate portions of these simulations in a way that speeds up the overall simulation. For example, in climate models, one big source of uncertainty and computational intensivity is modeling clouds. Clouds have a lot of microphysics going on, and some clouds can actually warm the planet because they're dark clouds that sort of trap heat, and other clouds can cool the planet because they're bright clouds that reflect sunlight. And these cloud physics are actually really expensive. So, there are a number of researchers at the moment who are trying to use AI and machine learning to maybe approximate the physics of any individual cloud and stick that machine learning approximation back into the broader climate model in order to speed up the extent to which it runs. Similarly, on the energy side, there are various folks who are trying to approximate various physical constraints that exist within the energy model, and similarly on the city planning side. So lots of places in which we have some kind of physical model. The goal isn't necessarily to replace that physical model, because in some sense, the physics themselves are really, valuable and hard to fit a full proxy to. But where we can somehow replace or approximate portions of these models in a way that maybe makes them a little less precise or a little less accurate, but allows the whole thing to run much more quickly. So these are some themes for how kind of AI can help address climate change. And again, I was only able to go through a few illustrative applications, but I hope that these were hopefully useful in sort of illustrating the breadth of the kinds of things that AI and machine learning can do, whether it is, again, providing information to some kind of decision maker, the first two themes here, actually optimizing or operating a real world system, the third and fourth themes here, or somehow facilitating scientific and engineering workflows that are meant to contribute to climate action, sort of the last two bullets here. And in terms of the applications I talked about, a lot of these are actually deployment ready. There are kind of existing AI, machine learning, and data science tools that we can already kind of employ to make a lot of these workflows happen. And people have in fact done that, as per some of the examples I talked about in terms of nonprofits and startups that are operating in this space. In addition, for those who sort of work on, developing new AI and machine learning methods, there are also lots of opportunities for innovation. For instance, a lot of the areas I talked about, climate science, energy, transportation, are either physical or engineering domains where it's really necessary to combine knowledge of your underlying data with knowledge of your underlying physical or engineering system. So there's been a lot of work on, for example, hybrid physical modeling in this area. Similarly, in a lot of the places where AI and machine learning are feeding into some kind of decision-making process, interpretability or uncertainty quantification within these workflows becomes really important, because the decision has to be understandable to or auditable by, for example, a policymaker who then actually employs that AI or machine learning aspect. And similarly, there are lots of applications of techniques in transfer learning and causal inference and in many other sort of new and cutting edge areas of AI and machine learning to actually address problems here. So the figure on the slide is actually a table from the paper on tackling climate change with machine learning that basically takes some of these areas of innovation on the columns and takes basically different kinds of ways in which we can facilitate climate change mitigation and adaptation and broader action on the rows, and actually tries to provide a little bit of a mapping at a glance between some of these techniques and some of the applications in a way such that if you're somebody who works on one of the columns, then that allows you to maybe identify where your particular set of skills or can actually play a role. So I would definitely encourage you again to check out this table within the paper or the interactive summaries that I mentioned before, which allow you to filter similarly. So that was an overview of the ways that AI can help, facilitate climate action. And before moving on from this section of the talk, I want to give one very concrete example, a category of example from my own work in terms of the kinds of opportunities for innovation that actually exist. So in particular, as I mentioned earlier in the talk, my work specifically focuses on how can you use AI and machine learning in the electric power sector. And the goal specifically is how do we manage electric power grids in a ways that allows us to more effectively incorporate renewable energy like solar and wind into these power grids. And the big methodological theme that my work tries to address is the fact that many climate and energy problems in the electric power sector, what I work on, but also more broadly, involve some notion of physics or hard constraints or decision-making procedures on the underlying system that need to be respected. And that, raw data-driven methods sometimes have difficulty respecting. So for example, I work on, again, electric power systems or electric power grids. And when I talk about electric power systems, what I'm talking about is the system through which our electricity is produced and then transmitted along lines and electrical equipment, and then eventually consumed by end-use consumers like us. So for context, as we saw in an earlier slide, electric power systems make up about 1/4 of global greenhouse gas emissions. And reducing these emissions means integrating low carbon sources of energy like solar, wind, and nuclear into the system. And solar and wind, and some other sources in particular, are very variable in terms of how much power they produce at any given time. In general, managing electric power grids is really difficult because they're subject to various kinds of physical constraints. For example, if I put power into the power grid, it flows along the power lines according to the physics of the underlying grid. There are various kinds of hard constraints, things like a particular power generator can only produce a certain amount of power or can only change the amount of power it produces by so much from one moment to the next. Or you also have to respect various kinds of stability constraints that exist on the grid. And if you don't satisfy these constraints, then that leads to multi-day blackouts and loss of lives on the power grid, which is not something that you want. There are also lots of decision-making procedures that come into play when you're trying to figure out how to actually manage this system. So for example, if I have some forecast of electricity demand, and I have some forecast of how much solar and wind power there might be on the grid, how do I schedule the rest of the power generators in a way that maintains the balance between supply and demand that we need, as well as satisfying various other physics that we have on the grid? So today, when we think about managing an electric power system that can deal with these physics and hard constraints and decision-making processes, this is done using traditional optimization and control methods. And unfortunately, while these methods have worked well in the past, these methods are, today a bit too slow or otherwise just failing to deal with the speed and scale that introducing new low carbon energy sources introduces into this system. And so this has led for a call for new methods, particularly from AI, which is potentially a good candidate to provide, fast, dynamic, data-driven methods to deal with this new complexity and speed at which we need to manage the power grid. But as I mentioned before, today's AI and machine learning methods generally tend to struggle with these physics and hard constraints and decision-making procedures that are so important to not breaking the power grid. So how do you actually reap the benefits of AI while still respecting and sort of satisfying all of these, existing considerations that exist on the power grid. So to give two examples of how AI and machine learning have been proposed here, one need here is that AI and machine learning techniques can potentially help adaptively control power generators, power inverters, batteries, all of these kinds of things on power grids in a way that is really dynamic and data-driven and can deal with things like a changing amount of renewable energy on the power grid in a very fast manner. And this is what AI and machine learning techniques are good at, but the limitation is that they're bad at enforcing the physics and hard constraints associated with the system. Another example of how AI and machine learning have been proposed to be used on the system are, as I mentioned earlier, forecasting. For example, to forecast electricity demand or to forecast electricity supply. And this is potentially a very obvious application because, AI and machine learning are very widely used for time series forecasting. But even here, there are some potential difficulties associated with this, which involve the fact that AI and machine learning methods for forecasting are often trained, to optimize some kind of metric like accuracy, even though that's not the metric we necessarily care about on the electric power grid. For example, if you're forecasting electricity demand, under-predicting electricity demand might cause you to underschedule power generation in a way that's really, really bad for the system. Whereas if you overpredict electricity demand, you might overschedule electricity supply, which is wasteful, but not necessarily as bad as having underscheduled electricity supply. And yet, in a kind of world where you're training your forecasting algorithm to be as accurate as possible, overpredicting and underpredicting electricity demand are the same. They have the sort of same implications from an accuracy perspective, but they have very different implications from a decision-making perspective. So how do you actually give your AI or machine learning model some information about how its forecast will actually be used downstream? And so my work tries to do is contend with these particular issues. How do you reap the benefits of machine learning or data-driven methods in these particular areas while kind of addressing the limitations that I've talked about here? And so what my PhD research focuses on is developing a framework called optimization in the loop AI that actually tries to address this challenge. And this is basically a framework for somehow developing AI and machine learning methods that incorporate knowledge of the physics and hard constraints and downstream decision-making procedures that I just talked about through the use of optimization problems. So for those of you in the audience who are familiar with the literature on, optimizing machine learning models or deep learning models, for example, gradient descent in deep learning, that's actually not what I'm talking about here. What I mean by optimization in the loop AI is that we can formulate optimization problems that capture the physics or hard constraints or decision-making procedures that we're hoping to enforce in a particular domain. And we can then embed these optimization problems either within, for example, our machine learning model or within the objective function that is used to help our model learn. So my work looks at this particular paradigm in the context of deep learning. So for example, here I have kind of visually a abstract representation of a machine learning model where X are the inputs to the model, H sub theta is the functional form of the model, or H is the functional form of the model, theta are the parameters of the model, H sub theta of X is the output, and then L is sort of the loss function by which we evaluate the quality of the output of the machine learning model. And when we think of a deep neural network, which is again the setting in which I do this kind of work, a neural network is just a bunch of nonlinear functions with parameters that are composed together, and we call these functions layers. The parameters of a neural network are updated using gradient-based techniques, using backpropagation and gradient descent. And so what this means is that every single component of our neural network workflow, every single layer and the loss function has to be differentiable. So what my work does is say, well, what I want to do is formulate an optimization problem that captures the physics and hard constraints that I care about. And I want to embed that optimization problem into the way that I design my neural network in the first place, as sort of a layer in my neural network. And in order to do that, what I have to be able to tell you is, well, I've now put this optimization layer into my neural network, but I need to update my neural network using back propagation and gradient descent. I need to be able to somehow differentiate through this optimization layer. So how do I actually do that? And so what my work does is proposes methods based on the implicit function theorem to actually enable you to differentiate through these optimization layers. And as a result, you can actually embed optimization problems within neural network workflows in various ways. For example, I gave this example earlier of how folks are trying to want to use AI and machine learning to control an electric power system in a way that satisfies the physics and hard constraints associated with the power system. So you might think of this as sort of a reinforcement learning problem where your machine learning model takes in some information about the state of your underlying system and outputs some information about the kinds of actions that you should take on your overall system. And what my work allows us to do is say, well, we can formulate an optimization problem that captures some of the physical constraints this reinforcement learning model has to satisfy, and then actually embed that optimization problem into our neural network model so that we actually have a reinforcement learning method that provably satisfies various kinds of physical constraints. So that's one example of just at a high level, how embedding an optimization problem into a neural network allows you to potentially come up with a method that is data-driven, is using data to actually figure out how to control a system, but inherently has some module within it that's causing it to enforce the constraints of the underlying system. Another example here is prediction. So I mentioned this idea that when we create some kind of prediction of electricity demand, we take in some historical data, we make some kind of prediction. What we care about is not necessarily the raw accuracy of that prediction, but how it actually informs the downstream decision that is made on the basis of the prediction. So if I predict some amount of, electricity demand is going to be on the system in the next hour, that informs the decision as to how much electricity to supply in order to meet that demand. And in a lot of cases, you can actually formulate the relationship between your prediction and your ultimate decision as an optimization problem. And so what my work says is, well, if I can have my machine learning model make some kind of prediction, and I can write down an optimization model that talks about how that translates, that shows how that translates into a downstream decision, then I can actually evaluate the cost of the downstream decision when it acts on the real system. So evaluate the quality of how I scheduled electricity supply when I see the true electricity demand, and actually back propagate through this entire workflow. So that was a really kind of quick dive into the kind of work that I do. And if you got a little lost in that, don't worry too much about it. The high level idea and the thing I was trying to give an example of is that as we try to, employ machine learning methods to decarbonize, for instance, electric power systems or other physics or engineering systems, many of these machine learning applications can actually benefit from incorporating physics, hard constraints, or domain knowledge inherently into the design of the machine learning method itself. And one mechanism, the mechanism I happen to work on, is by embedding optimization layers within neural networks. But in general, this area of physics informed or engineering constrained machine learning is actually really ripe for innovation, and the particular forms that it takes can really be influenced by the particular area you work on. So as you potentially work on applications in electric power systems or in forestry or so forth, the ways in which these the ways in which the machine learning methodological problems take shape are kind of unique and interesting in each of these areas. So zooming back out from electric power systems to this broader area of climate change and machine learning, I want to talk about some important considerations for doing work using AI and machine learning for climate action. So one thing that's really important to think about is as we, of course, employ AI and machine learning methods in real world workflows like the ones that I'm talking about, it's really important to think about how to do this in a responsible way. So this field of responsible AI is, of course, really interesting and important area of work, and it plays out in various ways in the climate change and machine learning space as well. For example, in this responsible AI space, there's a lot of discussion of how we actually reduce biases in the data that our machine learning models use and in the models themselves. And this comes up for sure in climate and energy workflows as well. For example, when we think about trying to use machine learning models to recommend how we should retrofit buildings to make them more efficient, it's important to think about how the data that we're using actually reflect the history of housing discrimination, for example, in the US, or reflect the fact that we actually have more data on buildings in certain geographies than others. And so our models might just not work as well for certain geographies. Similarly, even for sort of scientific models, things that we think of as not human models, but think of them as somewhat scientific. Even these are not devoid of various kinds of biases that are actually really important to consider. For example, as we create weather models or climate models or energy models, we often run some kind of physical simulation, and then we calibrate them based on some underlying data to understand whether our model actually did well. And this calibration is often actually optimized for particular regions. So if you look at, for example, European weather forecasting models specifically, they're calibrated then on European weather data, which means that they don't perform uniformly well across all regions of the globe. In particular, these tend to really fail on Arctic and Antarctic regions. So really important to think about how the certain kinds of data and modeling assumptions that we're actually making induce various biases in the applications that we're actually doing. In general, across climate and energy workflows, improving trustworthiness and accountability, again, a theme that comes up generally in responsible AI, also becomes very important here. For instance, as we manage electric power grids or industrial operations, we want to make sure to not break these underlying systems. So considerations of safety and robustness become really important. And similarly, interpretability and auditability are very important in policymaking contexts, where, for example, an AI or machine learning algorithm is informing a policymaker as to some kind of decision that they're making. AI and machine learning also have lots of implications for equity. And in the climate space, this also plays out in the area of climate justice, which basically is concerned with the fact that the impacts of climate change are disproportionately borne by the people who did not actually contribute to climate change themselves. And it's also really important to make sure that those stakeholders are part of strategies to actually shape and inform climate action. So as a result, it's really important when we think about using AI and machine learning in climate and energy workflows to think about, which stakeholders' problems are we actually solving? Are we kind of picking stakeholders of convenience who happen to be nearby or happen to have the funding to actually fund our research? For example, are we doing agricultural optimization just for industrial agriculture? Are we also thinking about smallholder farmers who may not have various kinds of funding and resources, but who nonetheless would also need sort of access to and could benefit from these kinds of methods? Similarly, are we centralizing power in the way that we actually do AI and machine learning, given that certain sets of entities with knowledge and power and that are often concentrated in the global north have a lot more access to various kinds of knowledge, computational infrastructure, and so forth that are needed to develop AI and machine learning methods? How do we actually make sure we do this work in a way that democratizes access to the capacity and computational infrastructure that's needed to actually fundamentally contribute to developing this kind of work? And then finally, or almost finally, avoiding digital colonialism, by which I mean, historically, of course, many colonial powers, they would take from the countries that they were colonizing various kinds of resources, use those to benefit the colonizers in a way that left the colonized really bereft of any of the benefits of those resources. And we can think about, do similar patterns actually play out with data? For example, as we think about home energy data that's available across the world, certain countries, for example, the US and Europe, have various kinds of protections on how that data can be used. And other countries like India do not necessarily have the same kinds of protections on how that individual energy data can be used. So it's important to think about, well, we want our AI and machine learning workflows to be representative of a broad swath of people. So we want to make sure that we're using data from a lot of different contexts, but we also want to make sure that we're not in some sense taking advantage of the fact that certain places have, fewer privacy mechanisms in order to experiment basically implicitly on various populations in a way that then primarily benefits strategies for other populations. So important to think about that. And then, finally, one thing I should mention is, of course, that AI and machine learning are, by no means a silver bullet. They are not necessarily always the most appropriate or, relevant strategy to use for any given climate related strategy. And so it's really important to think about, avoiding techno-solutionism, avoiding this idea of, I'm going to come in with AI and save everything. But instead be really, measured and careful about how we actually talk about this and think about this, and do this in close collaboration with various kinds of stakeholders who would actually, be affected by, or who should be part of developing various kinds of solutions in this area. So I know that we're sort of getting towards the end of the time here. So I'm going to really quickly go through kind of the other aspects that I talked about here. So as I mentioned earlier, I focused mostly in this talk on the ways that AI can be actually applied to help climate action, but there are lots of other ways in which AI interacts with climate change. For instance, as I mentioned earlier, there are lots of AI applications that increase emissions. For instance, AI is really significantly used to accelerate oil and gas and mining applications that are very emissions intensive, with some estimates mentioning that AI technologies have boosted production levels in some cases by, as much as 5%, and has, potentially generated billions and billions of dollars in revenue for the oil and gas industry. And we definitely need to be thinking about, well, if AI and machine learning are being used in such force for these kinds of applications, are they actually, impeding the transition to low carbon and renewable energy in these cases? There are also lots of applications that we don't necessarily think of as climate relevant, but that are. So for example, when we think about autonomous vehicles and ride sharing, these have various implications for, how much we actually drive as a society, whether we prioritize private and fossil fueled vehicles, or whether we actually try to shift to public transportation. And the way we kind of develop autonomous vehicles and ride sharing technologies can have huge implications for this in a way that it's really worth thinking about. How do we actually shape these applications? Similarly, AI and machine learning through personalized advertising and on-demand delivery definitely play a role in increasing societal consumption in ways that are not necessarily always correlated with happiness, but that definitely are correlated with emissions increases. And again, it's worth thinking about how we actually shape these applications in a way that is more aligned with climate action. AI and machine learning kind of, have a big role in information and misinformation and polarization online, including on climate change related aspects. And as I talked about earlier, AI and machine learning have a lot of implications for who holds various kinds of capital, knowledge, power in society due to who has access to these kinds of technologies. These impacts are really hard to measure, but they're of course very important to account for and shape. And then last but not least, AI and machine learning technologies themselves have a computational and hardware footprint that is worth thinking about. So on a macro level, this footprint is actually, relatively speaking, not huge. So data centers account for about 1% of global electricity consumption. And even though the sort of amount of compute that we're using has increased over the last decades, the kind of efficiency improvements of hardware have actually kept pace with this pretty nicely, though we can't necessarily take for granted that that will continue to happen. The greenhouse gas emissions here depend on, the amount of electricity you consume, the carbon intensity of the electricity. So does it come from renewable energy or fossil fuels? And also what it took to actually produce the hardware that you're using, and the fact that, hardware is replaced very frequently. There are lots of emissions associated with that. Now, AI accounts for some fraction of this small percentage. So again, on a macro scale, At the moment, AI and machine learning technologies don't necessarily make up a ton of the emissions, but we do need to drive this sector to net zero, and we necessarily can't take that this fraction stays small for granted. In particular, we are seeing, a large growth in the size of the largest models that we have in AI and machine learning. There are equity considerations in addition to emissions and considerations associated with this, given that large models are just more expensive to train, and as a result, not everybody can do that. And so then there's, of course, a lot of importance in pursuing energy efficient modeling, cost benefit analysis, for trying to trade off between accuracy and efficiency, doing work on measurement and reporting of these kinds of emissions in order to monitor the dynamics in the sector and also shape them going forward. So to kind of pose some takeaways here, whether or not you work on climate change, if you work on AI, your work probably has some kind of implications for climate change. And so it's important to consider the emissions impacts of your work in terms of both its compute and its applications. Think about the climate equity related implications of this work, and also just communicate responsibly about the limitations and capabilities of AI and machine learning, given that a lot of people are looking to AI and machine learning as a potential, savior in various sectors. It's very easy for them to latch on to various narratives about, AI does well in this particular way. Okay, great, it's going to save us all. So it's of course really important to communicate responsibly about these aspects. So I guess last but not least, for those of you who are interested in thinking more about these various kinds of issues or talking more with others who are thinking about them, I would definitely encourage you to check out the community and resources available through Climate Change AI, a combination of educational resources, workshops, funding, online community platforms, and all of that sort. So kind of information for those is on the slide. So thanks so much for listening. Sorry to run long, and I welcome any questions in the time we have left.
Great. We have time for one or two questions. I have one in person here, Evan.
Hey, thanks for the talk. You've given me some more thoughts on a topic I'm already very passionate about. This is a really, really high level question, but I was just curious, what's your thoughts on the lowest hanging fruit? So is there something that you see as something that we're close to being able to get to zero or negative relatively quickly? Thank you.
Yeah, so that's a great question on lowest hanging fruit. I guess there isn't an easy answer to this. And so I guess what I'll say is, for those who are thinking about working in this area and are thinking about what is the easiest place for my skills to be applicable, I often recommend sort of a stakeholder-driven approach. So, do you know people who work in the transportation sector, who work on energy, who work on these various issues, and can you team up with them? Because fundamentally, we need these technologies and these strategies to be employed across many different sectors, and we need different people to be working on different things. And you're going to be the most successful basically if you're working with people who have knowledge of these various sectors and can actually co-create with them. So I would say definitely like the stakeholder driven approach is the lowest hanging fruit from an individual perspective, in the sense that that's where you'll be able to make the most impact faster.
Great, thank you very much. Unless there's no more questions, since we're at time, I want to thank you, Priya, for a really wonderful talk that surveyed a very broad landscape. And I'll just say, as somebody who's using ML and AI to design better materials for energy and biology to eat and utilize methane, I feel seen by your talk. So thank you very much. And let's all thank Priya again.
Thanks. All right, thanks everyone.
Wonderful, thank you so much. And this ends our formal program, and this is our last seminar of the year. So I will see you all in the fall. Have a wonderful day.